All right, students were reminded the M&M lab is due today, dead tomorrow. Students were already given time to work on part A of 1.14. I reminded you all that your real focus should be the numbers that I've highlighted in orange. That's the data that you need. And the goal here was to explain where the percentages A, B, C, D, E, F, G, and H came from using the numbers that I've highlighted in orange. Okay, and it's just to impress upon you all that the orange is the actual data. Those are the actual counts. Everything else in the table was a number that was calculated based on the numbers I highlighted in orange. So you all could, in theory, recreate this entire table yourselves if all I did, and technically speaking, I don't even need to give you the totals. Technically speaking, those are the only numbers I need to give you. That's it. And that's the raw data that was collected. For every passenger on the ship, we needed 2 pieces of information. What class were you? And did you survive or did this person die? So if I gave you just those 8 numbers, you're going to recreate this entire table. Now, the table helps you with certain, once you build certain distributions, it allows direct comparisons to determine was there independence or dependence between the variables class and type. And those are the variables that we're dealing with in this case. 2 variables, folks. Class, you're either first, second, third, or crew, and survival. You either were alive or you were dead. There were 6 variables. That's a common mistake I get a lot of people making. Okay, because they're thinking alive, dead, first, second, third, crew. They're thinking 6 different things. No. If I'm looking up the history books of a passenger on the Titanic, I only need 2 pieces of information for them to be part of this data. What class were they? That's question number 1. And did they survive or not? That's question number 2. Those are my 2 variables. Okay? Now, to further understand this, I want us to put into words what A, B, and C represent. And I started my sentence structure with the percent of, the percent of, the percent of. Okay, now we're going to look at these 3 percentages, 16.6%, 41.4%, and 5.4%. Now I want to be clear, every single one of those numbers was focused on that count. Every single one of those percentages used 118 as its numerator. Your own answers, 118 over 711, 118 over 285, 118 out of 2201. Every one of those percentages was fixated on second-class people that survived, or that were alive, whichever word you want to use. Okay, second-class people that were alive. So those are the words you're going to use to explain every single one of those numbers. Now, I'll take a volunteer for the other 2, but I'm going to share my answer to A. A is a percent of row. So I'm only fixating my attention on the people that actually survived. I don't care about everyone on the boat. The 6.6% is a percent of row. I'm going to narrow my focus to only the people that survived. I don't care about everybody else. And I'm going to of survivors that class. And that's what I need to put into a sentence. So the percent of survivors that were second class. Now, how about for B? I'll take a volunteer for that one. Go for it. All right, I heard the percent of second class people total. To me, that would actually be this divided by that. Okay, the percent of second class people total is about 12.9% because 12.9% of the people on the boat were second class. But that doesn't explain the 41.4%. The key word missing, or the key concept missing in that answer was survival. Okay, so every one of our answers to this question down here has to involve the language of second class and somebody who is still alive, somebody who survived. Okay, take another shot at it. Go ahead, Amy. There you go. So it's pretty much exactly what I said, but you switch the vocabulary terms. Instead of the percent of survivors that were second class, it's, switch it, the percent of second class that survived. And understand those are 2 very different things. One of those numbers, the first one, would show up in sort of a segmented bar graph that focuses on the distribution, okay, of class. Whereas this is going to show up, the second one is going to show up in the distribution of survival. Those are 2 very different numbers. One says, only look at survival. Tell me what chunk of them were second class. The other says, look at all of second class and tell me what chunk of them survived. Those are two very different concepts. How about the third one? Go for it. Very close. I like that she had those in one big term, but I don't know the group we're talking about. It is the percent of second-class survivors. But from what population? Go ahead. Of everyone involved. I said passengers. If you said everyone involved, if you had said of all the people on the boat, I needed the definition of the group we're focusing on. So I use the word passengers. You could say everyone on the boat, whatever, however you want to say it. The percent of passengers. So everyone was a passenger. All 2,201 of them were passengers. What percent of everybody on the boat were second-class survivors? Okay. Now, what we're going to practice on the next page, once again, is looking at different distributions. And I'll tell you, there's a question I want to ask about on the second page once we finish it. It's not actually on the page, but it, in my way, really ties things together in an important way. Because the bottom line is, I'm trying to get you all to a point where I can present to you data like this. And, you know, if I'm being nice, I'll give you a graphical display with it. If I want to test your ability to build a display, that might be a task on an upcoming quiz. Like, here's some data, build me a display. Okay, but ultimately what I want you to be able to do is look at a chart like this that cross compares two, and does it between these variables? Does it seem like they're dependent? Or is it just kind of everything is the same across the board and it seems like they're independent? Okay. Questions on this page before I turn the page? And you should too. All right, turn the page. So same exact chart, different questions though. And again, when we're done with this page, I'm going to have sort of a all-encompassing question to ask. So the first one says, provide the marginal distribution of survival as percentages. Now, I understand there's a lot going on there that you need to pay attention to. You need to understand that marginal means you're looking at everybody. Okay, percentages is a specific way of providing the data. But the key thing I want to focus on here is distribution of survival. If I ask for distribution of survival, how many numbers are you supposed to report to me? Not 111. That's way too high. I heard another answer. 4 is a great answer. It's wrong, but you're on the right track. If you say 4, then what I'm assuming you're imagining is distribution of class. Class is a variable, first, second, third, and crew. So when we get to the next question that asks about distribution, if I were to ask, well, how many numbers does that mean you have to give me? Your answer is 4. Because if you're going to show of class, you need a number for each option within that. So 4 numbers. Got it. All right, thank you, Claire. So in this case, we're going to need 2. Now, let's be clear. If you only give me this, the people that were alive is 32.3%. You are not going to get full credit. I say this because this is a common mistake. People hear distribution of survival. They stated on the word survival. They forget that they're supposed to be giving a distribution of that variable. And they say 32.3% of people survived. You're not getting full credit because what's the other side of that coin? Okay? The other 67.7% of people died. That's a full answer. Okay? And again, I highlighted the percentages in blue because that is the way that you were specifically told to report this data. Give it to me as a percentage. Now, the next one I kind of already gave away. Question? All right. So the question was, anytime we see the word marginal, do we need to be thinking the total in the table? My answer to that was yes. With the next one, I already kind of gave away. We're going to want 4 different numbers. First, second, third, crew. Notice my labeling of FSTC because I was being lazy. Now, you're asked to provide this distribution as frequencies. Remember, frequencies is just a fancy word for give me the numbers, give me the counts. Okay? If it said relative frequency, well, now you have to calculate. Again, you have your options, fractions, decimals, percentages. But frequency is just a fancy way of saying how many times did this happen. Okay? So I take everybody on the ship and I break them down by first, second, crew, and I'm just giving the counts. Everything I put in red is a relative frequency. Now, the next two, same concept as before, meaning we're talking about distribution of survival, distribution of class. So we're still in a position where we need 2 numbers followed by 4 numbers. Okay, but what's more critical to me is that we understand this is a conditional distribution. The moment you hear conditional, I want you to realize I don't care about everybody on the boat. I care about some kind of subgroup. And by the way, this is typically how you make a comparison. You look at a distribution that's marginal. What happened to the entire population? Then you look at a subgroup and see, are they showing the same breakdown? That's one of the key ways that you test for independence. You look at what happened to everybody, and then look at the breakdown of a subgroup and see if they're the same. Okay, and if there's a difference, well, then you can argue dependence. Okay, now this is a condition in this case, because we're still doing distribution of survival, still 2 numbers, but the condition is your second class. So now what I'm telling you for this particular question is most of this table doesn't exist. That's what I'm basically telling you with that question. I want the distribution of survival on the condition that you're second class. So look at only those 285 people and tell me what percent of, well, I think it says counts. I think it says counts. So take those 285 people and break them into 118 were alive, 167 were dead. That's the answer to part C. Again, because the direction said counts, it would be wrong to provide a fraction or decimal or percentage, even though technically speaking, the mathematics in the red boxes is accurate. Mathematics in the red box is good, but because of the directions, it would be marked wrong. Okay? And now provide the conditional distribution of class among those that died as relative frequencies. I want you all to have a shot at this yourselves. Go ahead and write down those numbers. So before we get to the next page, I have one sort of follow-up question I wanted to ask that ties all of these together. You could use these distributions to make comparisons in order to justify whether or not you think type and class are independent or not. Okay, so you could use these distributions to make that decision. Right now, I would argue it's impossible because they're in completely different formats. Some of them are percentages, some of them are counts, some of them are decimals with the way I presented the blue. So for the purpose of this question, I want us to imagine that we're fixating on one type of data, percentages across the board. Okay. Now imagine you built a segmented bar for each of these displays. You build a segmented bar for the marginal distribution of survival, a segmented bar for the marginal distribution of class, and so on. You built a segmented bar for every one of these. Can anyone name 2 of these? And you can literally just say A and B, B and C, B and D, C and D, whatever you want to say. Can anyone name 2 of these that you could actually compare in order to make that judgment call about whether or not class and type are independent? Go for it. C and D, I would not be able to compare because one is a distribution of survival, the other is a distribution of class. So if you're trying to compare those, I would argue it's similar to trying to compare the first bar here to the first bar there. It's like 2 completely different variables, can't make a direct comparison. Take another one. Go for it. So I heard first and crew. What I'm looking for, though, because it sounds like you named 2 specific classes, I'm asking you to name 2 of these distributions, A, B, C, or D, that you could use to compare. Clara? A and C is one of the answers I would take, A and C. If you compared these, remember, the top one, A, is a marginal. The top one is, this is what in general happened to everybody on the boat. In general, 7% of them died. If you then compare that to, well, what happened within second class, you would notice so you could compare these and say, well, this is what happened to everybody in general on average, but this is what happened within second class. So when you compare a marginal to a conditional, as long as they're both similar distributions, they're both distributions of survival, you can make that direct comparison. Does that make sense? Okay, and by process of elimination, because I said there were 2 pairs, you could also compare those. You could say, all right, well, in general, remember, B is marginal. This describes the people got on the boat. In general, this is Now, if you then look at the distribution among those that died, what you'd want to see is that this distribution is exactly the same as that one. Okay, you'd want to see that they match or less, meaning each of the numbers are within 5%. That would suggest, doesn't matter if you're first, second, third, or crew, your chance of dying was basically the same because 14% of the people on the boat were first class and 40% of the people that died were first class. But of course, that didn't happen. You do see 5% differences or more. Bless you. So fixating on the first numbers that I just mentioned, well, in general, 14.8% of the people on the boat were first class. But when you fixate on those that died, they're underrepresented, which literally shows first class is less likely to die. Good? So when you're making comparisons, think it is totally fine to compare marginal and conditional distributions. In fact, that's typically what you would do. Okay, you can compare two conditional distributions if you wanted to. But the thing that has to remain the same is they have to be talking about the same variable. They have to be talking about the distribution of class, or both have to be talking about the distribution of survival. You can't take one of each and think you can compare them. All right, go ahead and turn the page. All right, I'm going to give you all another 4 minutes to read, think, talk, write. Your goal here should be get through part C. I'm going to walk you through the display. Just get through part C. Read, think, talk, then write. All right, so I gave students a few minutes to work ahead of me on 1.16. I asked you all to get through part C because I wanted to walk you through a couple principles on the display itself. Okay, so again, the first one is a marginal. It says, according to this data, people in general, 17% of them are smokers. Now, we don't see a single 5% differential from that. So let's be clear, if you went out and got your own sample of 1,049, we don't expect you to get exactly 16% of the females are smokers and 18% of the males are smokers. We expect you to see slight fluctuations. And when your data is within 5%, again, that's a very arbitrary limit. We'll get more formal with it second semester. But if your data sets are within 5%, we would say, all right, well, if you went out and collected the data again, that's close enough that maybe it would fluctuate the other way. And maybe even though you had fewer female smokers in this group, maybe when you go out and get another data set, you get like 17% of the females are smokers and only 16% of the males are smokers. You're going to see slight fluctuations. So if you don't see at least a 5% difference, you don't really have evidence of dependence. Okay? If you see a difference, think dependent. If you see a difference, think dependence. Okay? So in this particular case, if you did this, which is more or less beautiful, it's still missing two very important elements. Teo, what's up? So 5% for now is an arbitrary limit. When we get into second semester, we're going to do a probability analysis. And what we're going to ask ourselves is, what is the probability of seeing a difference of 2% in a sample this size? And if that probability drops below 5%, which is actually related to the normal curve, which is something we'll get into in the future, then we'll say, all right, well, the chances of seeing the difference you saw is less than 5%. So it would happen less than 1 in 20 times. And that's rare enough that we're going to conclude this probably didn't happen by chance. Like it probably happened because there's something going on. Okay, yeah. What two things are missing, folks? Go for it. Percentages. I have no idea what these percentages are. So please do not forget these percent labels. Hey, where's my other one? Come back. Are you hiding? There you are. All right, so give me those percentage labels. What else is missing? Yeah. You got it. I have no idea if the shading is smoking or if the unshaded is smoking. I need a key. Okay? Now, again, because you do not see differences, and when I differences, again, at least 5%, well, then your answer to the question, does it seem like sex and smoking habits are dependent? The answer is no. Now, in green, I've included what I have noticed is a really common habit that a lot of my students have. I don't know where you all learn this, but it's not necessary. It's regurgitating the question. The question was, does it appear that a person's choice to smoke depends on their sex? And so if you say to me, no, it does not appear that a person's habit of smoking depends on their sex, my reaction is, okay, you were fighting. You could have just said no. That was the question. Go right into your equation. The proportion of smokers among both men and women are roughly equal. And then I give the numbers. So notice I gave you the 3 elements I'm looking for. I answered the question. No. I gave statistics, 16 to 18. They're all kind of close. And I explained what the heck does that mean in context. And what it suggests is that in general, men and women have about the same chance of smoking. Questions? All right. So what I'd like you all to do is before next class, just read the chart on the next page and complete A, B, C. That's it. Do A, B, and C before you come to class tomorrow, because I'm going to start with a couple questions on this table and those answers. All right. Anyone watching the recording? Thanks for watching. Have a good one.